Right, in this video, we're going to talk about section 7.3, dealing with estimating a population standard deviation or variance. And what we'll do in this video for this section is to construct a confidence interval estimate of a population standard deviation or variance and be able to interpret such confidence interval estimates. Now, we already talked about how to estimate a population proportion and a population mean. Now we're going to look at a population standard deviation or variance. All right, so here we're going to present methods for using a sample standard deviation or sample variance, which is S squared. And the sample standard deviation, by the way, is denoted by lowercase s to estimate the value of the corresponding population standard deviation, which is sigma, or the population variance, which is sigma squared. And the methods of this section require that we use what they call the chi-square distribution. Okay, and chi is the Greek letter pronounced chi. Right now, the main concepts are these. We're going to look at point estimate, and then the confidence interval, and then the chi-square distribution. Now, the point estimate, of course, we're going to use the sample variance, which is S squared, as the best point estimate or single value estimate of the population variance sigma squared. And the sample standard deviation, S, is going to be commonly used as a point estimate for sigma, even though it is a biased estimator. We'll just use that as the point estimate for sigma. Confidence interval is this: when we construct a confidence interval estimate of a population standard deviation or population variance, we construct that interval using the chi-square distribution. By the way, this is the Greek letter for chi, and then the exponent of 2 is square, chi-square. And of course, here we're going to find critical values for chi-square. All right, so the chi-square distribution, if I can lift this up, is this. Now here we're going to use the formula for the chi-square, and that is, of course, n minus 1 times s squared divided by sigma squared. N is the sample size, and then s is, of course, the standard deviation, but when you square it, you're dealing with the sample variance. That's going to be divided by sigma squared. That's, of course, the population standard deviation squared, or the population variance. And to find the critical values of chi-square, we denote a right tail chi-square value, a right tail critical value by this notation, chi-square on the right, and we denote a left tail critical value by chi-square on the left. Okay, and these are the notations here. Now, those critical values can be found by using either technology or table A-4. And in this case, table A-4 is included in these notes. So this is what table A-4 looks like, the chi-square distribution. And it does mention something at the very top that is very important that you need to know, that it's going to be the area to the right of the critical value. Okay. Now, in table A-2, when we were dealing with the standard normal distribution, we were dealing with the cumulative area on the left. Table A-4, which is your chi-square distribution, deals with the area to the right of the critical value. That's very important. Okay. And in table A-4, they do require that we first determine the value for the number of degrees of freedom. And of course, we did something before where we had to find out the number of degrees of freedom. Okay. Now, if you remember that the number of degrees of freedom, or DF, for a collection of sample data is the number of sample values that can vary after certain restrictions have been imposed on all data values. So in this case here, the number of degrees of freedom will be the sample size, which is n minus 1. The degrees of freedom is always one less than the number of whatever your sample size is, one less than your sample size. So you have to do n minus 1 to get your degrees of freedom. All right, and these are the properties of a chi-square distribution. All right, the chi-square distribution is not symmetric, as you can see here in this illustration. Unlike the normal and student t distribution, the chi-square is not symmetric. So as the number of degrees of freedom increase, the distribution does become more symmetric. And number 2, the values of chi-square can be 0 or positive, but they can't be negative. Okay? Chi-square will be 0 or a positive number. They're never going to be negative. The chi-square distribution is different for each number of degrees of freedom. So as the number of degrees of freedom increases, the chi-square distribution approaches the normal distribution. So here, this will be a chi-square distribution for 10 degrees of freedom. That's the one you see in blue. The one that you see in red represents the chi-square distribution for 20 degrees of freedom. Now, because the chi-square distribution is not symmetric, a confidence interval for sigma squared does not fit the format of this. So here we have to do separate calculations for the upper and lower confidence interval limits. Okay. Now, since we're going to be using table A-4 in this video to find critical values, we're going to note the following design feature of that table. And this right here is very important. In table A-4, each critical value of chi-square in the body of the table corresponds to an area given in the top row of the table, and each area in that top row is the cumulative area to the right of the critical value. Okay, and it mentions that in table A-4, you're dealing with an area to the right of that curve. Now, a word of caution is this. Table A-2 is for the standard normal distribution, and it provides the cumulative area from the left. But table A-4 for the chi-square distribution uses cumulative area from the right. Okay, I mentioned that earlier. So that's the difference between those two. Don't get those confused. Okay. Also, we can use technology to find critical values of chi-square. But one major advantage is that the technology can be used for any number of degrees of freedom and any confidence level, not just limited choices included in table A-4. And another major advantage is that you can often generate the confidence interval without going through the steps of finding the critical values and manually calculating the confidence interval limits. Okay. But in this video, we're going to go through those procedures here that I will show you shortly. Okay, so here we're going to look at finding a confidence interval for estimating a population standard deviation or variance. And this is on the next page. And I have provided notation here that we will be using. Like sigma is the population standard deviation and S is the sample standard deviation. Sigma squared is the population variance and S squared is the sample that should read sample variance and not sample standard deviation. So let me correct that. sample variance. N is the number of sample values and E is the margin of error. And this notation, that's the left tail critical value of chi-squared. That's why you see chi-squared with a little L in your subscript. And chi-squared with the R as a subscript, that's going to be the right-tailed critical value of chi-squared. There are two requirements. One, you must have a simple random sample, meaning that samples of the same size have an equal chance of being selected. And number two, the population must have normally distributed values, even if the sample is large. Okay. The requirement of a normal distribution is much stricter here. So that means departures from the normal distribution can result in large errors. So this is a strict requirement. Now, for the confidence interval, if you're dealing with a population variance or sigma squared, this is the format for it. N minus 1 times S squared divided by the chi-square value on the right. That's going to be less than sigma squared and less than N minus 1 times S squared divided by the chi-square value on the left. Now, this might look backwards, but if you think about it, if it's done this way, you'll see that this will be the lower limit and the one on the right will be the upper limit. Okay. But for a confidence interval for a population standard deviation or just sigma, it's just simply taking the square root on the left side, the middle, and the right side of this compound inequality. You'll get this. The square root of N minus 1 times S squared divided by the right tail critical value of chi-square. And that's less than sigma, which is your population standard deviation, and less than the square root of N minus 1 times S squared divided by the left tail critical value of chi-squared. We're going to be using this right here. Now for the round off rule. That's going to be this. If you were using the original data set, more than likely we won't in this video, but let's say you had an original data set. To do that, you have to round your confidence interval limits to one more decimal place than used for the original set of data. So if your data set is all whole numbers, then you're going to round your limits to one decimal place. Or if your whole data set was to one decimal place, then your limits would be to 2 decimal places, and so on. But here we're going to be using some of the statistics like the sample size and the standard deviation for constructing the confidence interval. We're going to round the confidence interval limits to the same number of decimal places used for the sample standard deviation. So if that sample standard deviation is to 1 decimal place, our confidence interval will be to 1 decimal place. Or if it's 2 decimal places for your sample standard deviation, your limits will be to 2 decimal places, and so on. And here's the procedure for constructing the confidence interval for sigma or for sigma squared. And it's this. You want to verify that the 2 requirements are satisfied. And then you're going to use N minus 1 degrees of freedom, use technology, excuse me, or refer to table A-4 to find your critical values. Your left tail critical value of chi-square and the right tail critical value for chi-square that correspond to the desired confidence level. You'll evaluate your upper and lower confidence interval limits using this format of the confidence interval, and that's the format you'll use here. And then number 4, if a confidence interval estimate of sigma is desired, take the square root of the upper and lower confidence interval limits and change sigma squared to sigma. And number 5 is on the next page. Round the resulting confidence interval limits using that round off rule. Okay, that is, you're going to round your confidence interval limits to the same number of decimal places as you have for your sample standard deviation. All right, now, word of caution is this, that confidence intervals can be used informally to compare the variation in different data sets, but the overlapping of confidence intervals should not be used for making formal and final conclusions about equality of variances or standard deviations. All right, so now let's look at example 1. Let's apply that procedure that just presented in this example. Use the given information to find the number of degrees of freedom, the critical values for chi-square on the left and for chi-square on the right, and the confidence interval estimate, sigma. It is reasonable to assume that the simple random sample has been selected from a population with a normal distribution. So in this case here, we got the nicotine and menthol cigarettes. Our confidence level is at 95%. The sample size is 26, and the sample standard deviation is 0.28 milligrams. Okay. Well, if our sample size n is 26, we can easily find out what our degrees of freedom is going to be. That's going to be n minus 1. And n is 26, so 26 minus 1 will be 25. So we got 25 degrees of freedom. And also our sample standard deviation is 0.28 milligrams. Now on the right side of my I'm going to draw a chi-square curve. Looks like this. So now I'm going to need to know what the chi-square critical value will be on the left and the chi-square critical value on the right. I'm going to shade the area to the left and to the right. So here's the right side, and this is the left. Now, we're dealing with the 95% confidence level. The 95% in this curve is in the center. That's always going to be like that when we're doing a confidence interval. All right, your confidence level will be in the center. The shaded areas represent the remaining part of that curve. Keep in mind, the area under the curve is 100%. So if this is 95%, these two shaded areas represent the remaining 5%, split evenly. So that means if I split 5% evenly, then that means that this shaded area on the left is 2.5%. And this shaded area to the right is also 2.5%. All right, so this is where we're going to be using table A-4 in this case. So now I'm going to find I'm first going to find the chi-square value on the right, because if that's 2.5%, let's write that as a decimal as 0.025. You can take your calculator, do 2.5, and divide that by 100 when you convert from a percent to a decimal. So you have 2.5, divide that by 100, you'll get 0.025. Now, for our chi-square value on the left, is all the way to the right. Keep in mind that it's going to be that your chi-square value represents area, cumulative area to the right. Well, to the right is 95%, and I also have 2.5%. So 95% and 2.5% added together will be 97.5%, or 0.975. Now, another way you could have gotten that would be this. If this area to the left of this chi-square critical value to the left is 2.5, and the area underneath the entire curve is 100%, 2.5% from 100% will give you 97.5%, or 0.975. All right, so now we're going to use table A-4 to get the chi-square critical value on the left and the chi-square critical value on the right. Let's start with the chi-square critical value on the left. We have 0.975 here, and our degrees of freedom is 25. So I'm going to switch over to another screen to get my table here. So here's table A-4, the chi-square distribution. Now, we have 25 degrees of freedom, okay? So here I'm going to highlight 25, which is right here. And to the right was 0.975, if you remember. And also, I had 0.025. I'm going to highlight that as well. All right, so now, if we go to the right, go to, let me change this. It would go 2.25 and 0.975, read across and then read down. You're going to see that this will be the critical value on the left. That's going to be the chi-square critical value on the left, which is in this case 13.120. Here it is. As you're going across and down, it will be 13.120. So for the chi-square value on the left, so let me go back to this. The chi-square value on the left would be 13.120. Now for the chi-square value on the right, now if I go back to that table, all right, if you read across on the line where it says 25 degrees of freedom and the column for 0.025, you'll see this will be your other critical value. That's going to be the chi-square value on the right, which is 40.646. Okay. So the chi-square value on the right would be 40.646. Okay. So again, this is 0.975 and 25 degrees of freedom. Read down and across, that's 13.120. And then we got 0.025 here. Read down and across, that'd be 40.646. Okay, so those are my chi-square values on both the left and on the right. Now I should be able to construct my confidence interval, which is going to be this, the square root of n minus 1 times s squared, all divided by the chi-square critical value on the right. That'd be less than sigma and less than the square root of n minus 1 times s squared times the chi-square critical value on the left. Now let's do our substitution here. Let's see, n minus 1, well, n is 26 minus 1 times s, which is 0.28. But that's going to have to be squared. Because notice they only give you the sample standard deviation. This calls for s squared, so you have to take that sample standard deviation value and square it. Divided by the chi-square value on the right. That's going to be 40.646. And then less than sigma and less than the square root of, well, the n minus 1 times s squared, the numerator, that's going to remain the same. 26 minus 1 times 0.28, and that's squared, all divided by the chi-square value on the left. That'd be 13.120. And now we're going to use our calculator to simplify this, okay? All right. So in this case here, the square root is second x squared, or the square root. And then our numerator, I'm going to put this in parentheses, 26 minus 1, close parentheses, times 0.28. And then I'm going to hit the x squared button because it has to be squared. And then that's going to be divided by 40.646. And then hit enter. Now, our sample standard deviation is to 2 decimal places. So the upper and the lower limit needs to be rounded to 2 decimal places. So 0.219 rounded to 2 decimal places will be 0.22. Then that's going to be less than sigma and less than. Now, instead of entering all of this again, and that's because that numerator is the same, this is what I'm going to do. I'm going to do second and enter. Second enter gives me this back, but I'm going to change that 40.646 and type in place of it that chi-square value on the left, 13.120. So I'm going to use my left arrow key and then type in 13.120. Use the right arrow key to get out of the radical and then hit enter. And to 2 decimal places, this will be 0.39. All right, so that's going to be my confidence interval for this situation. And if we want to interpret that, we need to say this, that we are 95% confident that the true standard deviation of nicotine in menthol cigarettes falls between 0.22 milligrams and 0.39 milligrams. Okay. So that's how we do a confidence interval for a population standard deviation. Here's another example. Here we're going to use the given information to find the number of degrees of freedom, the critical values on the left, for chi-square on the left, and for chi-square on the right, and the confidence interval estimate of sigma. It is reasonable to assume that a simple random sample has been selected from a population with a normal distribution. So here we're dealing with platelet counts of women, and our confidence interval, our confidence level is 95%. The sample size is 24. The sample standard deviation is 65.9. Okay, so now, if that's the case, if n is 24, we can find out what our degrees of freedom is going to be. That's n minus 1. So 24 minus 1 will be 23. So I'm going to be dealing with 23 degrees of freedom. And of course, my sample standard deviation is 65.9. Okay. There's my chi-square curve. So I need a chi-square critical value on the left and a chi-square critical value on the right. I'll even shade those areas to the right and to the left. The 95% is in the middle. Everything on the whole curve has an area of 100%. So that means 95% from 100% is 5% split in these two shaded areas. So that means this left side is 2.5%. The right side is the other 2.5%. So if I want the chi-square value on the right of that is 2.5% or 0.025. And for the chi-square value on the left, I have to include the 95% and the 2.5%, which gives me 97.5% or 0.975 as a decimal. Again, you can do this. The 2.5% that's on the left side to get the part that's on the right, the percentage on the right, 2.5% from 100% will give you that 97.5% or 0.975. All right, so let's start by using table A-4. Okay. Exit that out. All right. Now I'm still using 0.975, that's shaded, and the 0.025, that's also shaded. This time it's only 23 degrees of freedom. All right, so here's 23 degrees of freedom right here. And now 0.975. If we go down and across from 23, this will be the chi-square value on the left, which is 11.689. That's the chi-square value on the left, 11.689. And for the chi-square value on the right, I still had 23 degrees of freedom, but to the area to the right was 0.025. If I go down and to the right, this would be my chi-square critical value, 38.076. Okay. So let's go back here. The chi-square critical value on the left was 11.689. And the chi-square value on the right chi-square value on the right was 38.076. Okay. Now I had that information, I can go ahead and construct my confidence interval estimate. So this will be the square root of n minus 1 times S squared over the chi-squared critical value on the right. That's going to be less than sigma and less than the square root of n minus 1 times S squared divided by the chi-squared critical value on the left. All right, so let's do some substitution. Our n was 24. So I had the square root of, this is going to be 24 minus 1 times S, which is 65.9, and that's squared, divided by the chi-square value on the right, that's 38.076, less than sigma, less than the square root of 24 minus 1 times 65.9, that's going to be squared, divided by the chi-square value on the left, which is 11.689. All right, so now let's do our calculations here on the left and on the right. So here, second x squared. Then I'm going to put 24 minus 1 in parentheses times 65.9, and then that's squared, divided by 38.076. Now to 1 decimal place, since our standard deviation for the sample is to 1 decimal place, our limits will be to 1 decimal place. So 51.21 would be 51.2. And then that's going to be less than sigma and less than. Now the 1 here, this one, I'm just going to do second and enter, since that numerator is the same. The denominator would just be different. So I'm going to change that 38.076 to 11.689. Then hit enter. And to 1 decimal place, this will be 92.4. And this is our confidence interval. And to interpret that, we can say this, that we are 95% confident that the true standard deviation of platelet counts of women fall between 51.2 and 92.4. Okay. Here's another example. A simple random sample from a population with a normal distribution of 107 body temperatures has the mean 98.90 degrees Fahrenheit, that's X bar, and S equaling to 0.66 degrees Fahrenheit. Construct a 98% confidence interval estimate of the standard deviation of body temperatures of all healthy humans. Okay. Now, let's take what we have here. We have a sample size of 107. Simple random sample of 107 body temperatures. We're told that X bar is 98.90 degrees Fahrenheit. Since we're estimating a population standard deviation or variance, we do not need to use that 98.90, which is the mean. Okay. Sometimes it's good to have that information, but when we're doing a population standard deviation, its confidence level, interval, we don't need that information. We only need the standard deviation of 0.66 degrees Fahrenheit. And since n is 107, our degrees of freedom would be n minus 1, or 107 minus 1, which is 106. Okay. And from here, we can find our chi-squared critical values on the left and on the right. Okay. So we need a chi-square critical value for the left tail and a chi-square critical value in the right tail. All right. And we're dealing with a 98% confidence interval. So 98% will be in the middle. The area underneath the curve is 100%. So subtract 98% from 100%. That's 2% split in these two tails. That means the left tail has 1%, the right tail 1%. The chi-square value deals with the the area to the right. So the chi-square value for a right tail, that's the 1%, or 0.01. For the chi-square on the left tail, in the left tail, again, we're looking at the cumulative area to the right of the chi-square critical value on the left. So 98% and 1% is 99%, or 0.99. Do this all the time. All right, so now going back to table A-4, we're dealing with 99 and 0.01. Okay. Clear these out. Let's see. We have 106 degrees of freedom. Unfortunately, we don't have 106 on here. So if you were restricted to this table, the closest value you'll have to use is 100. So we have 100. We'll use 100 degrees of freedom right here. All right. And now, let's look at this. We're dealing with 90.99, which is right here. Oops. All right, let me use a different color. Let's try yellow. All right, 99 will be here. Or better yet, let's just circle it. And 0.01, that's here. All right, so if I do this, all right, if I go down to 0.99, here's what I need to do. All right, so if I go down to 99, all the way down to 100, this will be my critical value for chi-square on the left. 70.865, 70.065. And then this will be the chi-square value on the right, which is in this case 135.807. Okay. Okay. I might have to show you on here because I have 0.99 right here. And if I go all the way down to 100, that will be the 70.065, which is the chi-square critical value on the left. And of course, for 0.01, that's here, go all the way down to the bottom, you'll see that it is 135.807. Okay. Those are my critical values for chi-square on the left and on the right. And then we go ahead and do our confidence interval, which is this, the square root of n minus 1 times s squared divided by the chi-square value on the right. That's less than sigma and less than n minus 1 times s squared divided by the chi-square value on the left. Okay, and then do our substitution here. All right, the n is 107 minus 1 times s, which is 0.66, and that's going to be squared, divided by the chi-square value on the right is 135.807, and that's less than sigma and less than the square root of. Now the numerator is still going to be the same, so I'm copying that over. The denominator is going to be different. The chi-square value on the left, that's 70.065. And then we calculate our upper and lower limits. All right, so we do second x squared for the square root. In parentheses, it'll be 107 minus 1, close parentheses. Oops. Then times 0.66 and square that, divided by 135.807. Now, our standard deviation is to 2 decimal places, so our limits needs to be to 2 decimal places. So this will be 0.58 to 2 decimal places. And that's going to be less than sigma and less than. I'm going to do second and enter. Change the denominator of 135.807. I'm going to delete this to 70.065. And to 2 decimal places, that would be 0.81. Okay, so that's our confidence interval for this situation. And if we want to interpret that, we can say that we are 98% confident that the true standard deviation of body temperatures of all healthy humans falls between 0.58 degrees Fahrenheit and 0.81 degrees Fahrenheit. Okay. Now, usually with this, you will have a problem using table A-4. If you were trying to get a more accurate confidence interval, you could use technology like StatDisk, which is what I'm going to show you how to use StatDisk for this particular situation. All right. So I'm going to go to this screen right here. Now you should already had signed up for StatDisk. All you have to do there is just pretty much go to statdisk.com and then just sign up for it. It's an easy thing to do here. Okay. So once you logged in, go to analysis, and then we're going to go to confidence intervals. Click on that. We're going to pick the one that says standard deviation 1 sample, because we're only dealing with 1 sample statistics here. You'll select that. You should see this screen here. That's where you enter your confidence level. They have 0.95 as a default. We're dealing with a 98% confidence interval, but 98% as a decimal would be 0.98. You'll just type that in. Tab down to the sample size. The sample size, which was n, that was 107. Then you had a sample standard deviation, which is S. That was 0.66. You'll type that in, click on the green button that says evaluate, and you'll get two confidence intervals, one for the standard deviation and other ones for the variance. We're only dealing with the standard deviation in this case. So they round this off to 5 decimal places, 0.56867, less than your true standard deviation and less than 0.78415. Okay. Now, here's off by a little bit because we use a conservative degrees of freedom of 100. They're using the exact degrees of freedom of 106. We had to enter the sample size, which was 107. So usually StatDisk does give us a more accurate confidence interval. Okay. All right, now let's look at example 4. A chocolate chip cookie manufacturing company recorded the number of chocolate chips in a sample of 70 cookies. The mean is 22.84 and the standard deviation is 2.59. Construct an 80% confidence interval estimate of the standard deviation of the numbers of chocolate chips in all such cookies. All right, so in this case here, let's identify what's given. We do have a sample size N, which is 70. This is a sample of 70 cookies. The mean is 22.84, but that's not necessary when we're constructing a confidence interval using for a standard deviation. But our sample size, we need the sample standard deviation. We need that. That's giving us 2.59. Okay. If our sample size is 70, the degrees of freedom, if we were to use table A-4, that would be 70 minus 1, which is 69. So we're looking at 69 degrees of freedom. All right, so I'm going to draw the chi-square curve. I know I need a chi-square value on the left and a chi-square value on the right. And I'm dealing with tails on the left side and on the right. So I have left tail and a right tail, critical value for chi-square. Let's see, we're doing an 80%. So 80% is in the center. If the area underneath the curve is 100%, then 80 minus 80 from 100 will give me 20%. That 20% is split between these two tails. So that means there's 10% on the left side and 10% on the right side. Okay. So for the chi-square on the right, that's the 10% or 0.10. And the chi-square on the left, that's going to be the 80 plus that 10%, which is 90% or 0.90. All right. So here, this is where we're going to need to use table A-4 to get our chi-square values. Okay. Clearing all this stuff out. All right, so we got 9.90, which is right here, and 0.10, which is right here. Now, there's no 69 degrees of freedom here. So we're going to have to use a conservative number like, let's say 70%. I mean, let's use 70. Okay. So 70 is right here, and I'll go ahead and highlight that. Okay. So if I read across and down on that column, it'd be 55.329. That's going to be the chi-square value on the left. And this number right here under the column of 0.10 will be 85.527. That's the chi-square value on the right. Okay. Okay, so here we go. The chi-square value on the left is 55.329. The chi-square value on the right would be 85.527. Okay, so now let's construct our confidence interval. That's, of course, the square root of n minus 1 times s squared, all divided by the chi-square value on the right. That's less than sigma and less than less than okay times square root of n minus 1 times s squared divided by the chi-square value on the left. Okay, so that's the format for the confidence interval for a population standard deviation. Now all we have to do is just do some substitution here. The lower limit will be the square root of 70 minus 1 times s, which is 2.59. That will be squared divided by the chi-square value on the right. That's going to be 85.527. That's less than sigma and less than the square root of, the numerator is the same, 70 minus 1 times 2.59. That's squared divided by chi-square value on the left, 55.329. And then we go ahead and do the calculate those limits. Let's see, second x squared for the square root of, in parentheses, 70 minus 1, close parentheses, times 2.59, and that's squared, divided by 85.527. This will give me 2.326. Now, if we round this off to, let's say, actually the 2 decimal places, this will be 2.33. Okay. That's less than sigma and less than second x squared for the square root. Change this to 55.329. That will be, in this case here, 2.89, rounded to 2 decimal places. Okay. So if we want to interpret that, we can say that we are 80% confident that the true standard deviation of the number of chocolate chips and all such cookies falls between 2.33 and 2.89. Okay, now, however, we can do this by using StatDisk. So let me go ahead and go into StatDisk and show you how that's done. Okay, I still have my confidence interval for standard deviation one sample screen up from the last example. But if you need to get to that, you go to analysis, go to confidence intervals, click on that, go to standard deviation one sample. The confidence level, you're going to have to change 0.95 to 80% or 0.80. Sample size was 70. And then tab down to the sample standard deviation that was 2.59. And then click on evaluate. Okay. Here I was using StatDisk. Our confidence interval right here was a little bit more accurate than the ones that we use for using the table. Okay. So feel free to use StatDisk whenever necessary to try to get an accurate answer or an accurate confidence interval. All right, last we'll look at using confidence intervals for, well, actually determining sample size. That's the one I want to talk about because we can use StatDisk as well. The procedures for finding the sample size necessary to estimate sigma square are much more complex than the procedures given for means and proportions. Instead of using very complicated procedures, we will use the table below. Now, also StatDisk and Minitab release 16 or later also provide sample sizes. I'll show you that shortly in StatDisk. Excel, StatCrunch, and the TI-8384 Plus calculator do not provide such sample sizes. So on your handout, you'll see this table. On the left side is for sigma and for sigma squared. And here they're dealing with only this for 95% and 99%. Okay. So here to be 95% confident that sigma, that S is within these set percentages of the value of sigma, the sample size N should be at least those values given. So here's just one example of that on the next page. You want to estimate sigma for the population of IQ scores of statistics professors. Find the minimum sample size needed to be 95% confident that the sample standard deviation is within 1% of sigma. Find the sample size, and is this sample size practical? Well, here we can use this table right here. Okay, here we want to be within 1% of sigma, and we want to be 95% confident. So we have to use this part where it says 95% confident that S is going to be within 1% of the value of sigma. This is what your sample size should be. And in this case, it's 19,205. Okay. So here to answer that question, the sample size N should be, I'm going to use greater than or equal to for at least 19,205. Okay. However, we can get that from StatDisk as well. So let me quickly show you that. So here's StatDisk. Now, in this case, we're going to go to analysis. This time, we're going to go to sample size determination and then estimate standard deviation. Here it is. You'll get this screen. The confidence level that we're dealing with in this case is 95% or 0.95. We already had that in. Percent margin of error, we're dealing with they say within 1%. Here, they just want you to enter the whole number, not the percent as a decimal. So here we enter the number 1 as 1%. Then click on evaluate. Okay. So the required sample size to estimate the standard deviation would be 19,205, which is what was determined from that table that I showed you. Okay. So now the question is this sample size practical? I don't think it is, because it's going to be hard for you to find 19,205 statistics professors across the country. That's going to be hard. Okay. Okay, so that will conclude this video on section 7.3, dealing with estimating the population standard deviation or variance.